everyone, this is Alan Lee, and today I'm going to show you how to run the CREST model in a hands-on tutorial. So in this small project, we're going to focus on a flash flood event recently happened in Kentucky areas. So in July 2022, the copious rainfall in the central Appalachian area unleashed several flash floods, causing over 35 fatalities and many economic damages. Down below is the 3D terrain of the Jackson County. As you can see, this basin is a perfect example of a flash flood valley, meaning that the rainfall received over the mountainous areas can accumulate and drain the downslope into the lowlands, causing a flashy streamflow. So the question or the problem is, can we use the CREST or EF5 model to simulate this severe event? In doing so, we are going to prepare the data for CREST or EF5 model. The first one I'm going to use is the basic files from the hydrosheds.org website, including basin shapefile, digital elevation model, flow direction, and flow accumulation. The second, for the forcing data, we're going to use the multi-radar, multi-sensor rainfall product and the USGS global evaporation product. Of course, you can use other remote sensing or local gauges from public accessible dataset. But in this case, we're using the state-of-the-art radar gauge merged product in order to guarantee the quality of the simulation. And finally, we are going to use USGS stream gauges as observational values to validate the simulation of our model. So the first step is to download some basic files. The first one is the basin shapefile. So since we determined our area of interest to be in the Jackson County, Kentucky, so we're going to type in Jackson County, Kentucky in the search box. Then you navigate to this location. Then we can simply draw a extent of this location. And we're going to use the data hydrography. Then once you click it, it will expand. Then we'll select all. We'll use the HUC 8 sub-basins. So basically, the United States is divided into several basins, and from HUC 2 to HUC 4 and HUC 8, once you increase the numbers, you get much higher resolution or small extent of the basins. So you subdivide by 2 into those large basins. And for the file formats, we're going to use the shapefile. Then we're going to click search products. It will wait a few seconds to find the suitable product you want to use. Then here, as a result, you can see there are several basin shapefiles, and we're going to choose the one that suits our problems the most. So if you zoom out, so you can see there are some overlapping basins, but in this case, we're gonna just use this one, 05100201, since it covered the Jackson County as well as some downstream sites. Then we just download the link as a zip file into a folder. Here I'm gonna use the flash floods, this whole folder. I already downloaded this file, so no worries, I'm not gonna download it again, but for you, you should be able to download this and extract the zip file using your Windows default zipper. Okay, so since we have the basin shapefile already, we need to clip those basin digital elevation model, flow direction model, and flow accumulation model into the basin extent. So we're gonna need to download the basin files from this hydrosheds.org website. If you click this, it will go to this website. Then you click products for the Hydrosheds, and then there's some there's a download page. Go to the data download page. There are several options. One, conditional DM, flow direction, flow accumulation, and void fill DM, etc. But in this case, we're going to only use the conditioned DM, flow direction, and flow accumulation data from this website. Then if you click it, it will expand several continents according to the extent of your research area. So the one I'm going to use is North America. Expand this. And there are some coordinates associated with this zip files because it just divides those basically the whole extent region into sub areas in order to store those large files. And according to the research area we're choosing, so I'm gonna go ahead and use this north 30 degree and west 90 degrees zip file. If you're not sure, which file you're gonna use, you can just import your base and shape file into a JS software and find out what is the coordinate or bounding box coordinates of this shape file. Then you can find a coordinate file based on that. Since already downloaded those files here in this folder, as you can see, accumulation, condition, DM, and flow direction. So I'm not going to download it again, but for you, you should be able to download those files smoothly. Then we're going to use some geographic information systems to process those data. The one I'm going to choose is called the Quantum GIS. It's basically free and open source geographic information system software. It has several options. It has Mac OS, Linux, and Windows version of this software. So you can use the latest release of this QGIS software download to your local computer. I already have it, so I'm gonna just launch a QGIS software. Then the next step is to clip the raster data into the basin extent. So once you have the QGIS software installed and opened in your local computer, there we go. Then you can, in this browser, you can click this browser and navigate to your folder. So basically, we're gonna load the zip file into the main canvas. So this is the main canvas where you can visualize all your geospatial data set. So here is the basin zip file I downloaded from that website. Then accordingly, I need to load, import the flow accumulation data. So this is the zip file. If you click this triangle icon here, it will expand and show you the TIFF file. That is the one we need to clip into the basin extent. So basically just load, import those files into this main canvas. And then we can go to layers, put this basin shape file on top, so it can show in the top layer. Then from the processing toolbox, if you don't have it, you need to go to this menu, find the processing, and click the toolbox icon. So the first time you may not have that toolbox, but once you click it, it's a pop-up window on your right. So basically, we're gonna search for clip raster, then just click clip raster by mask layer. Then first, let's do the conditional DM. The mask layer, we'll use this basin shapefile. The projection, we're going to use 4326. That is a uniform word projection, and assign a negative values to the low data value, where we just use the negative 9999. And for the advanced parameters, you click that. The output data type should choose float 32. That is the data type is required by the software, and we save to the file. So this is the flow condition data. So we're going to use just name it to any type of any name you want. Here I just use DM Hydrosheds and save. It already exists, but I will just replace it. So make sure you have everything set up, then just click run. So that's all for the data, the DM data that I processed. I'm going to repeat this process for the other three for flow accumulation, the same setup, but you need to change the file name to, here I used FAC, then finished, then repeat this for flow direction. But for flow direction, we're going to just use -1 as no data values and rename it to F3rd. So once you finish it, if you unclick these files, you should be able to only say the, for instance, this is the flow direction within only the basin extent. So it's not showing the whole global or large extent values. Once you've done that, you should be able to find those files in your folder. Then for the next step, we're going to use some forcing data. And so first step is to download the rainfall data from this website. That is where the MRMS multi-radar multi-sensor rainfall product is stored. I'm going to search for 2022 in July, and basically from July 25th to 30th. So we'll find the MRMS and click unzip, and we use 1 hourly multi-sensor COPE quantitative precipitation estimation in this link. So you have to click each one of them in order to download. Click one and store in your computer, and just do this for the following days, not only 25th, but from 25th to 26th, 27th till 30th. So basically I already downloaded those files here in this folder. The next step is to convert those files into a GeoTIFF format, because basically first the files you downloaded are based on grep, that is zipped format of the file. So you need to unzip it and then export it into a GOT format. So here, for instance, this is the one we have. That is the July 20th. You can download from July 25th, but I just already have many others. Suppose we have, let's say, four files here in these layers. What we're gonna do is to go to the processing, go to the raster and click conversion, then translate. Instead of running one by one, we can run as a batch process. So you can click the plus icon, then it will just generate other placeholders for other files. So the first file, the July 20th, this first hour, second hour, third hour, and you can use this is uniform geospatial projection, and you can click autofill and fill down because they are the same. No data value, we don't need to specify that, and just no converted. Here the converted, you can create a folder called MRMS. For instance, to demonstrate that, we're going to use MRMS, maybe new. Then here the file name, you can leave it as a blanket. Oh no, you cannot, just MRMS. Then it asks you to whether you want to autofill. So if you say yes, we want to fill with parameter values, that is a parameter from the input data, input layer. So if yes, just use the same file name from your input file, but instead it will just add the T file to the end. So basically, as long as you have as many geospatial rainfall data as possible, then you can run it. Click run. You don't have to clip into the basin format in this way because the software itself can handle this for you. So after this, you can see we have 4 generated geospatial GeoTIFF file from this data. This is a format that the EF5 or CREST program can read. So suppose I already have all the files needed. Then the next step, we're gonna download the potential evapotranspiration data from this USGS website. Since the potential evapotranspiration data does not vary much by hour, so we're gonna just download the daily data from this period, 2022 July 25th. I'll click download. July 25th, then download data. So basically I already have the evaporation data downloaded in this folder here. But once you extract those files, the raw format is in .bil. That is not readable by the EF5 or CREST software. You still need to translate or convert these files into GOT format. So basically what you will do here is that you import the files that you need to convert into the layers. And again, go to raster, conversion, translate. You can do a batch process. Just add as many as you want. And then you just repeat the process we did for rainfall product. Then you should be able to generate those T files listed here. Once you have done that, that's good for the forcing data. Then this slide just shows how you can follow the steps that we mentioned previously. And then next is to find the USGS gauges so that we can use that values to validate whether our simulation is biased or correct. So we need to find the strain gauges inside the basin of your choice. But first thing, you may not be able to know how many gauges are within your basins or whether there's any big gauges within your basin. What we suggest you to do is that you have this code, basically have this code. You can just search here stream gauges. Then within some, they're basically, this is a USGS website. It will pop up some gauges within your area of interest. So for instance, this one, 03 to 77300, that is within Kentucky River. That's North Fork, Kentucky River at Whitesburg. If we click this link, it will go to the data download page. We'll only select the discharge and use a table format. Tab separated format. And the begin date is from July 25th. That is when we have our rainfall data from, till July 31st. Then click go. So this is the data that we have output, but it's not it's only a web page. We need to save this as a TXT format into our folder. So I'll name it as 03277300.txt. Once you do that, you can find this file in the folder, and I'm gonna open it with my Excel, and those basically just some metadata or just information. We can simply delete those rows, and only this first column is USGS. That doesn't mean much, so we just delete it. This is site number, and you can leave it as it is, but does not contain much information. We only need the width, date time, and the values. So we just delete those columns. That does not mean much. One thing you need to pay attention to is that this gauge data is in local time format. So for instance, this is Eastern time, but the results we generated from a EF5 or CREST model is from a UTC time, universal time. So basically, you need to convert this Eastern time into a UTC time. One simplest way is that you can shift those columns by the time difference. For instance, the Eastern time will be, it has 4 hours difference to the universal time. So we can just select this column. You can press Control Shift and down arrow. It will select the whole column. Then you can just simply drag it and shift by 4 hours. So the previous first hour, 0 hour of July 25th is becoming the 4 hour July 25th. And you can leave those cells as empty, and finally delete this one. For the date time, it should be good. So you can save it as a comma separated format, that is CSV. Just recommend use MS DOS format, then save the same name. So after that, you should be able to get this file exported. That is a CSV file from your previous text-based file. Then finally, we're entering the final stage that edit the control file. So the control file is basically where you tell the model what you want to simulate and what you want the model to do, right? So basically, there are 4 sections or 5 sections that you need to modify. One is called basic section, forcing section, gauge section, CREST parameter set, the parameter section, and the final task section. The basic section is just providing information regarding the basic form files, and the forcing section is to provide information regarding the rainfall and evaporation information, and the gauge is to provide information regarding gauge location and file location. The CREST parameter set is to provide some parameter values for the water balance, and of course you have other routing models. You need to provide parameter sets for the routing. The final task is to say whether you want to do a pure simulation, or is it a calibration problem or a warm-up simulation. So I have my control file opened here. So within the basic, there are DM, DDM, FAM. You need to specify the location of your GOT files that we converted previously. Here I just, because it is within the same folder, they're in the same folder of my EF5 program, so you don't have relative paths, just name it here. But if it's not in the same folder, for instance, the MRMS data we stored into a folder called MRMS, you need to specify the location here, or the evaporation, you need to specify the location. And for the projection, I used the geographic projection. If you follow my steps, it should be remain the same. And S3 DDM equals true if you download data from the Hydrosheds as we did. So you basically can leave those as unchanged. And the precip forcing, you need to just fill in those information. For instance, the type, that is the GOT, the unit is in millimeter per hour, the frequency is 1 hour, it's hourly, the location is in the MRMS folder, and the name. For the name, you need to replace the year, month, and day, hour as this placeholder. That's why the program can read in this format. You can provide as many precipitation data sets as possible. Here I just provided two, but you can just only use one if you only have one precipitation data set. And next is a potential evaporation. Again, type in the format. The format is in GeoTIFF. The unit is in millimeter per 100 days. Just be careful when you use this unit. So you need to, once you download the data, if you look at the ET data, the value ranges from 0 to over 1,000. You can basically inspect this pixel. You can find, we can just inspect the one in our basin. You can find the value is around 500. That is not a value for millimeter per day. It is in fact a value for millimeter per 100 days. So you need to prescribe that into this unit. And frequency is daily. Location is in eval folder. So that is 14 section we've done. Then the next is to specify the gauges. We need to type in the location of the gauges, latitude, longitude, latitude of this gauge, and the OBS is where you stored your CSV file. So if you follow my instructions, we store this CSV file in the same folder, so we don't any relative paths. Outputs equals true. That means you can output the observation dataset as well. Then basin area, you can basically find the basin area from the USGS website where you downloaded the gauge data. If you select all a summary of all available data for this site, you can find some information here. For instance, the longitude, latitude, but this is in a different format. You need to convert it into a decimal format. If you can Google it. And the drainage area is 66.4 square miles. You need to convert these square miles into square kilometers. If you type in the search box, it already converted for you. This is in square meters, but you need to divide it by 10 to the power of 6. So it's around 171 square kilometers. So in this control file, you need to specify the basin area 171 square kilometers here. Here I have some other gauges, but you don't have to if you only want to use the one gauge. And next we go to the CREST parameter set. That is where you have those parameters, parameter values specified. We just recommend you go to the GitHub to find out the United States parameter graded parameters. If you don't have it, it's fine. You can just leave it. You can just delete them and only specify those values. It basically means it's a lumped parameter for the whole basin. It's not divided by pixels. But here in this case, I just have this United States graded parameter sets I can use. And you do the same thing for the routing parameter. Just specify. At first, you may not have any idea how you change those parameters. You can just leave as default, and once you have some outputs, you can just change and tweak those parameters. For instance, you say that stream flow value is too high. That means there's not enough water infiltrate into soils. You can basically increase the FAC, which is hydraulic conductivity value. Once you increase hydraulic conductivity value, there's less water remained on the surface. Then it will decrease the stream flow values. But that's after you have some observations, you can change that. Then the calibration parameters, we can leave it as it is because we didn't perform any calibration yet. For the task, there are several tasks, but we only do the simulation task. So the style, you just type in simu, that stands for simulation. The model we use is CREST, and routing model is KW. The basin here, you need to be consistent with the basin you named here. So under the basin section, there's just basically the gauges you used in this basin. I use KY, so here I have to use KY. The precipitation, I use MRMS. This name has to be the same name as here, listed here. Then the PET, the same thing. I use PET 22, that is the name here. Then parameter say KY CREST, that is the name I specified here. Then same thing for kinematic wave routing parameter. The states is only for the project you have some warm-up period, so you will load the states as the initial estimates. But in this case, I don't have that, so it's fine, just leave it there because the program can identify whether you have those files. If not, it just ignores. And time step is 1 hour. The time began, I just use the 2022 July 25th till July 31st. And again, the state is the initial values, but I don't have it. Then the output, you need to create an output folder. Here I created my output folder. Here. And output grades, whether you want to export some GeoTIFF values, for instance, streamflow, but in this case, I just leave it as it is. Then once you save it, you need to execute this program, EF5 program. Then it will pop up a window saying some information, the DM is loaded, DDM loaded, then no errors. There's one error, failed to load some grid. That is fine, just some system information that in Windows 10 is different from previous Windows versions, so it has this automatic error message, but it's fine. The program is running. As you can see in the current time step, it just tells you when the program is at, so it's at July 30th. It's fairly fast for this project, even for 90-meter resolution. Once it's finished, there's a done message at the bottom, so you can tell if the program is finished or not. Once it's finished, in the output folder, it will generate some CSV files. So if you open this, it basically has a program generated CSV file for discharge, that is simulated discharge, and observed values, that is from the USGS stream gauge data we provided at this time. To plot these simulated versus observed, you need to just delete those non values because the plotting cannot recognize those NaN values. Then you're gonna insert a graph into scatter, and as you can see, this is way off for the streamflow simulation. But one thing you need to bear in mind is that the streamflow data you obtained from the USGS gauges, they're in the unit of cubic feet per second. In order to convert it to unit cubic meter per second, you need to multiply those values by 0.023 or something. You need to look it up in your calculator or even on the website. So these are the values that you should be able to get, and you can save it, then do the simulation again in order to provide some meaningful values. Delete this, save this, and I need to run this program again. So the program is running, and after that I should be able to get some meaningful values. So it's done, and let's open this file again. Delete those NaN values. Oh, it's not changed. Sometimes you cannot hold this Windows open because it wants write values into the open folder, because the program doesn't have permission to write one that is already open. So I'm gonna do this again. All right, go to output. Then, as you can see, those values are changed. Then we can plot, insert a plot. So this is what we get. The blue curve is what we simulated, and the orange curve is what we observed. In this case, we need to just tweak the parameter set, because as you can see, the flood peak is not well captured. But as you can see, there are some missing values as well. You need to go back and forth to change those parameter sets in order to get the flow adjusted or snapped to the real observed values. And in later sessions, we introduce a calibration, automatic calibration. You'll find that is a lifesaver, and it will just do the calibration itself, but it's covered in another session. That's all for today's hands-on session. I hope you find those materials useful, and let us know if you have any questions.